Okay, so good morning. Um, so I want to briefly explain the fusion of Bayesian optimization algorithm and the LSTM model. Alright, so I'll start by illustrating the Bayesian optimization algorithm first, and then I'll move to LSTM model, the algorithm, and of course, then the fusioning of both Bayesian optimization and LSTM. Alright, so starting with Bayesian optimization now. The first step is because there's no we'll talk about optimization, then we'll talk about objective function, and because basically that's exactly what we're trying to minimize or maximize already. Okay, so objective function f of x is the objective function representing the performance matrix of the LSTM with the hyperparameter x. Right? So what we are trying to optimize now is the LSTM hyperparameters. So we just want to be sure, we want to be able to get the hyperparameters value that will give us our LSTM model best performance, right? So the objective function is represented by f of x, and where x is actually the hyperparameters such as learning rate, number of people's batch size, the organization values, and so on and so forth. Alright, so in step 2, we try to define a surrogate model, which is the Gaussian process itself. Then the surrogate model is represented as f of x into the Gaussian process into m into x, comma k into s comma s bar, where m of x is the main function and the k x comma s bar is the kernel function. Alright, so that's the second step, which is to create or define our surrogate model, which is the Gaussian process itself. So then, of course, we all know that our base model is the LSTM, the long short-term memory. Okay, so then the next step is 3 acquisition functions. So we have many acquisition functions, but the one we are using in this research is expected improvement. So the acquisition function's name we are using is expected improvement, which is given as alpha of x is equal to e max a maximization function. So between 0, which is ranging between 0 f of x minus f minimum. Okay, so where f minimum is the minimum observed value so far. So the minimum observed value so far. So we are theoretically we are observing the value of x, which of course the x is the vector of all these parameters. Okay, so then the next step to that is step 4, which is next hyperparameters. So x next. So the next hyperparameter is given as x next is equal to argmax. Okay, x alpha of x. Okay, that's the formula for calculating the next hyperparameters. Okay, so then the final step under Bayesian optimization is to update the surrogate model. So we need to update the surrogate model. How do we do that? So after evaluating f into x of next, we update the surrogate model. So we are able to evaluate the next hyperparameters. Okay, so the surrogate model is updated by f new of x, which is the new hyperparameters we need to use to update the surrogate model, right? So it's equal to f old of x plus Gaussian process update is 7 to x of next comma f into x next. So that's the equation for the Bayesian optimization. Then let's move on to the LSTM model, right? So step 1, LSTM output. The output of an LSTM model with hyperparameters x is denoted as LSTM of x. Okay, so the output of the LSTM model with the hyperparameter x is denoted as LSTM of x. So that's the output of. So let's say the first iteration. So we selected using optimization algorithm or optimization Bayesian optimization. So we've selected some set of hyperparameters, right? So the output of that is denoted as LSTM of x. Okay, then the training loss now, because that's the objective function we are trying to minimize, right? So during the training we are trying to minimize the loss function. Okay, so it's denoted as L of x. So then the hyperparameters now. So S represents a set of hyperparameters for the LSTM model. Okay, so basically what we are trying to do is we are trying to use Bayesian optimization to fine tune our LSTM model. So that's just what we are trying to do. So let's look at the fusion of Bayesian optimization and LSTM model. Okay, so optimization process now. So now when we are combining the two together, the first thing is to integrate Bayesian optimization with the LSTM training process. Okay, so the process starts, then we integrate Bayesian optimization, and the essence of integration of that integration is for the Bayesian algorithm to be able to fetch or select all the hyperparameters, the configuration variables, okay, for the LSTM to be able to select the best values for each of these parameters. For example, the learning rate, the particular value you should take, regularization value, and the number of epochs, and so on and so forth. So we are looking for the best value for each of the configuration variables to train the LSTM model, and that's exactly what we are trying to do. So then at each iteration of Bayesian optimization, we select XNet. XNet using the acquisition function, which is the improvement, okay? So which is expected improvement. That's the name of the acquisition function we used. So then step 2, then we train the at each iteration of Bayesian optimization. We select XNet using the acquisition function. So use the acquisition function to select the next set of hyperparameter values. Okay, then we train the LSTM model with the hyperparameters that we have selected using the acquisition function. Then talking about the overall objective, to minimize the final performance metrics of the LSTM model by tuning hyperparameter through Bayesian optimization. So this process continues iteratively. Okay, so and it is defined as the mean of x into f of x is equal to mean x LSTM of x. So that's the overall objective. Then we then update the process. So update the Sogomate and LSTM model iteratively based on observed performance metrics. So iteratively as we are updating we update the surrogate model, which is by optimization or the Gaussian process. Okay, then we use that one. We use the equation, the expected improvement, to select the next type of parameters for the LSTM, and this goes on until we get to the best performance matrix, and then we can. So because we are going to be monitoring it manually, and of course, or we can set up some hyperparameters as well by doing a kind of callback, and then there's this configuration, early stopping. We can do early stopping. So once we get the best value for each of the configuration variable, then we use that to train the LSTM model. Then the LSTM, based on performance metrics we're using, for example, if we're using mean square error, then we begin to monitor it until when we get it, and because of the callback or the early stocking, so the system will be able to tell us, okay, this is the particular time that this is the best performance, and then we can now fix the values. So that's the level of fusioning Bayesian or combined Bayesian using Bayesian optimization algorithm to fine-tune our LSTM hyperparameter configuration. Thank you very much.